Hi, I'm Conlon Foster, and this is Lab 4, Sampling and Aliasing for ENME351. Here we see my Arduino code. We're doing this in 115,200 baud. In the loop, I have commands for two analog inputs measuring the potentiometer voltage and the analog signal. I use the potentiometer voltage to create a sampling frequency, and I put the analog signal into a string to send it to processing. The delay we see at the end is periodic dependent and changes with the sampling rate. The Arduino was set up in the configuration shown, and the processing code was unchanged from the downloadable VSA. First, we have an input signal of 75 Hz. We can see aliasing occur in the top two plots because the Nyquist criterion is not satisfied. The bottom two plots demonstrate our expected amplitude spectra peaks at 0 and the input frequency. When the input signal is 100 Hz, the same situation applies. Actually, the sampling rate of 198 Hz does not quite satisfy the Nyquist criterion, as it is not more than double the input frequency. However, if this were assumed to be a 200 Hz signal, then we can appropriately anticipate our expected peak of 100 Hz. 3 of the 4 sampling rates experience aliasing when the input frequency is 215 Hz. You can see an aliasing frequency is 19 Hz in the 98 Hz sampling instance, as demonstrated by the non-zero peak. If this signal were to satisfy the Nyquist criterion, then this peak would instead be 215 Hz. Finally, all of the sampling rates experience aliasing at an input frequency of 300 Hz. For the spectra plots that experienced aliasing, I calculated first the Nyquist frequency, and then by means of a folding diagram used that to calculate the aliasing frequency. In evaluation of my summary table, we can see that the aliasing frequencies I calculated are almost exactly in line with the peaks that I observed in the spectra plots. Although I am not positive, I think to attribute this to the delay microseconds command I used, which allowed for a higher resolution, and for the strong processing power of my own computer, which was able to appropriately allocate enough resources for the process. Going over our two types of plots, the frequency domain will display peaks at 0 and the input frequency if the time domain adheres to the Nyquist criterion. If it does not adhere to this, then the frequency domain will display peaks at 0 and at the aliasing frequency. For the first part of exercise 2, I was to create a square wave with a sampling rate of 500 Hz and an input frequency of 10 Hz. Here, we can see that reflected in the amplitude spectra plot, as the highest peak occurs at the fundamental frequency, 10 Hz. At every odd interval n, our amplitude decreases, and at every even interval n, the amplitude is 0. That is because we plotted a sine wave, or an odd function. The n-scope cannot output a square wave using the analog output, as a square wave is often a digital representation of an analog wave. In order to appropriately create the square wave, I generated a pulse output with an input frequency of 10 Hz. For clarity's sake, I set the duty cycle to 50%. The DC offset was also unchanged. For a Fourier series over an interval of 0 to 5, our output is exactly what we would expect it to be. Our DC offset is 2.5, and we have an odd sine function that decreases with n. For the triangle wave, I did not need to generate a pulse output, as the n-scope can do this through its analog output. The time domain here is reminiscent of what occurs if we were to sample at exactly twice the maximum frequency. In fact, if I were to speculate, that is how the n-scope software was able to generate this plot. For our amplitude spectra plot, we can once more see that the odd function plot observed by the square wave is mimicked here. The amplitudes themselves, however, are much smaller. This may occur as a result of the sharper changes experienced in the square wave as a result of it exclusively representing either a peak or a trough. If any clarity is required for the images or data shown here today, please reach out to me. Thank you.